So, number one, this is the questions from yesterday. Define acceleration verbally and mathematically. Acceleration is change in velocity divided by change in time, right? Mathematically, they want A equals delta V over delta T. What type of quantity is acceleration? It is a vector. How come, Dave? Because vectors have direction. Vectors have direction. Are you with us now? Okay, now you're with. What is deceleration? Negative acceleration, right? How fast something slows down. Or changes direction too, I suppose, really. A certain car is accelerating at 5 kilometers per hour per second. Explain what is happening to the motion of the car. I would like something like the car's speed is increasing by 5 kilometers per hour every second. Exactly. Give an example of a moving object that has a velocity vector and acceleration vector in the same direction, and one that has it in opposite directions. Brendan, I know you know this because we worked on it together. So if they're in the same direction, here's my car. Right? There's the velocity. There's the acceleration. This is a car that is speeding up. And if they are opposite directions, if the velocity is this way, and the acceleration is that way, then it's slowing down, right? Well, that is a slowing down. Can an object be moving at a constant speed and accelerating? Chandler knows. No. Can an object be moving at a constant speed and accelerating? At 3:50 today, you're going to be on that bus, headed home, making that turn at St. Rose. Can an object be moving at a constant speed and accelerating? Yes. If the direction changes. Remember that discussion, Chandler? If the direction is changing, constant speed, but yet still be accelerated. What would be the shape of a speed versus time graph for an object in free fall? Speed versus time. As something falls, it speeds up. Now, it actually speeds up, and we would say because it's down, right, the direction would actually be negative, right? So the velocity would be increasing in a negative sense. Would it be increasing at a constant rate? Would the velocity be increasing at a constant? You guys need to pay attention because it's listen time.
Is it in vacuum?
It's in a vacuum, Wyatt.
Yes.
Yes. So it would be increasing at a constant rate, and you're right, if it's not in a vacuum, then eventually it would reach terminal velocity. And what would the slope of this line be? It would be minus 9.8, right? Because the velocity of the paper clip would be minus 9.8 meters per second squared. Every second, the speed would increase by minus 9.8 meters per second. Monique's giving me that quiz look.
But like, if it's just speed and time.
Oh! Speed and time. Right you are. Mr. Bennett, you're wrong. It would be up. In fact, I would even argue it wouldn't even be up or down because it's not positive or negative. Yeah, I don't like that part. Good catch. Good catch. What is the relationship between speed and velocity? Well, velocity is simply speed with a direction. Exactly. Answer the following by referring to figure 3.5a. Oh, that's back of you, isn't it? 3.5a. Is there a 3.5b?
No, there's question A, question B.
Oh, I see. Okay, okay, gotcha. So 3.5 looks like this, right? We've probably seen this one before. Over which interval did the object have the greatest velocity? And this is what kind of graph? This is a position time graph, or displacement time graph. So when does it have its greatest velocity? When it's the steepest, and where would that be? I would say between C and D. Right? The slope of the displacement time graph is the velocity. Is it all coming back to you now? maybe nightmares. Over which interval was the object's velocity decreasing? Is it decreasing? Yes, I think it is. Right here, right? It's in here. How come? This is part A. How come in here? Because the slope is decreasing. Does it flatten right off? Not quite. If it flattens right off, then it would be going 0. It stops, wouldn't it? Original was the speed increasing. That'd be this interval right here, right? How can you tell? Slope is increasing. This is all that sort of whole week of stuff all thrown into one big review here. Last one, sketch a graphical motion. This is a function of time that would correspond to the following trip. You start the bicycle from rest, increase your speed until you reach a comfortable traveling speed. You continue at the speed for a few minutes and complete your trip by slowing down uniformly to a stop. It would be almost identical to this graph right here, wouldn't it? It'd be curved, and then it would be straight, and then you would stop. That was pretty easy, I think. Hopefully you guys did those questions. I'm hoping. Okay, let's go through this quick and then we'll go do our fire drill thing. Okay, so does this sheet look familiar to those of you that were here last year? It should. It's sort of the everything you need to know about graphs sheet, right? And it's so important that I hand it out again, because you probably didn't save your stuff. You probably burned all your physics notes, right?
I'm saving up for
Okay, anyways. Okay, so down the left-hand side, I would suggest you highlight or circle the top there, because the left-hand side of the chart is for what kind of graphs? Position time graph. So this basically tells you how to do everything. Okay, so down the left-hand side, because if you have a position time graph and you need to find displacement, and I also suggest to draw these little pictures on the side. If you need to find displacement from a position time graph, what do? You read off the final and the initial, and you simply subtract, right? Like if this is position 10 and this is position 2, well then the displacement is going to be plus 8, right? From 2 to 10. 10 minus 2. Right? This is a 10. That's 2. Right? Remember doing that sort of stuff? If you have a position time graph and you were asked to find average velocity and it's a straight line graph, what do? Find the slope. Pick 2 points. Find the slope. Do you remember how to find slope? Size over run, right? y2 minus y1 all over x2 minus x1. Find the slope. What if you have a position time graph and it's curved and you need to find average velocity? What do? Average velocity means take those 2 points, 2 endpoints, and find the slope of the line that you draw between the 2 points. That's the average velocity. The slope of the line between 2 points. Some of you are probably thinking, I thought we were supposed to find the tangent line. Tangent line is when you're finding instantaneous velocity. Instantaneous velocity. If it's a straight line graph, and you have to find instantaneous velocity, well that just means the slope right there, right, which is the same as the overall slope of the line, right? Rise over run. If it's a curved line graph, how do you find the instantaneous slope? That's the slope at an instant. That's where you do the tangent line. Do the little pictures help? They should. If you have a position time graph, flip the page over. I think it's on the back side, right? Still, does it say position time graph at the top? On yours? Does it say position time graph? No? Write it in. On the left-hand side, it's position time graph. Mine says position time graph on the top. If you are asked to find average acceleration, it can't be done. If you're asked to find instantaneous acceleration, it can't be done. Not without converting it to a velocity time graph. Okay, now let's go to velocity time graphs. Flip back to the front side. If you have a velocity time graph and you're asked to find the displacement, well then you have to find the area. Remember finding the area? Triangles and rectangles and such. Find the area. And if it's below, you find the area above, and it's negative, right? Remember that? If you have a velocity time graph and you're asked to find average velocity, how do you do it? You use v equals d over t. And where do you get the d from? Displacement, it's the area. D is calculated as shown in number 1. T is obviously time. If you're asked to find instantaneous velocity, it's easy. You just read it off the graph. How come? It's a velocity graph. That's how come. What is the velocity? You just read it off the graph. It's a graph of velocity. Read it off the graph. Who used to say that all the time? Me? No, there's some kid. I used to always ask him, they'd say, read it off the graph. Oh, maybe it was Wayne. Velocity time graph. If you're asked to find average acceleration, if it's a straight line graph, you find the slope. Find the slope. If it's a curved line graph, find the slope, but you got to draw a line between those 2 points and find the slope. Fire! Hang on, we'll finish. It's just a walkthrough.
But we're gonna die.
No, you're not going to die.
We're gonna go fire.
If you have a velocity time graph and you're asked to find instantaneous acceleration and it's a straight line graph, the A inst is equal to the A av. So in other words, find the slope. And if it's a curved line, again, you're finding the slope, but because it's curved, what do you have to do? Draw a tangent line. You should know all that. You may not remember it. We'll spend a little time on it. Let's go for a walk outside. Faster. Overall, the average was 64, with a standard deviation of 23%. That's pretty wide. That kind of means we're all over the place. Okay, let's take a few minutes and go through it, okay? We've got about 15 minutes here left. So, A bar from 0 to 4 seconds. How do you find average acceleration? From 0 to 4 seconds. So we're talking about this interval right here. Average acceleration from a VT graph is the slope. So we're at 10 to 2, so it's going to be 2 minus 10 all over. 4 minus 0 is going to be minus 8 over 4 or minus 2. The correct answer is A. Most people got that. That's good. Real good. A bar from 10 to 16 seconds. Most people got this one right too. That's good. From 10 to 16. And it's A bar, so average acceleration, we're talking about slope, average slope. To find average slope, you connect the dots, connect the endpoints, and find the slope. So we're up to 0, we started at 8. So 0 minus 8 all over, 16 minus 10. That's going to be 8 over 6, or 1.3 repeating. C is your correct answer. Coming back to you now. Number 3, delta D from 0 to 4 seconds. Delta D on a velocity time graph is the area, so 0 to 4 seconds. So we're talking about triangle above and rectangle below. Maybe you forgot the rectangle below. So the rectangle is up to 2 and over to 4. The rectangle is 8. The triangle is from 0 to 4, half the base. The height is from 2 to 10, that's 8. The base is 4. 4 times 8 is 32. Half of that is 16. 8 plus 16, 24. Correct answer should be B. We didn't do so well on that one, did we? Lots of people said minus 8. Sure how you got minus 8.
Yeah, I just went down.
What did you do?
I found out what I did wrong.
Don't guess. Delta D from 0 to 10. 0 to 10 is all the way to here. Delta D, so we got to find area here, here, all the way to there, this little guy right there, and this one here, which is negative, right? So what did we have before? We had 24 just here. Then we've got from 4, 5, 6, 7, that's 3 times 2, we've got 6 there. We got this little tiny guy right here. It's 5, 6, 7, 7.5. It's only a half times 2. I think that's plus 1 in there. And then down here, this is 1, 2.5 times minus 8. 2.5 times minus 8 divided by 2. Minus 4 minus 10. Right? 2.5 times minus 8 divided by 2 should be minus 10. 24 plus 6 is 30. 31 minus 10. Correct answer C, 21. Yay. Is that a hard one? Yeah? Did you do it in grade 11? Yeah? Do I expect you to know it now? Yeah. Am I okay with you not knowing it now? Yeah. So learn it, relearn it. 8 instant, 9 seconds. 9 seconds is right there. How do you find instantaneous acceleration? That is the slope. It's a straight line, so we just find the slope using the endpoints. That's minus 8, that's 2. So it's minus 8 minus 2, all over 10 minus 7 is minus 10 over 3, which is minus 3.3. A. Yay. Oh, lots of people got that. That's good. A instant 14. 14 seconds is right there. How do you find instantaneous? Here you're going to have to find a tangent line, which you're going to have to draw. Are we all going to get the same exact answer? Oh, thank you. 14, right there. Are we all going to get the same answer? No. But when you find the slope, I get an answer that's closest to 1.67, and most of you got that, so that's real good. B might be possible if you pick bad numbers, right? But certainly not A, because it's negative. V inst at 2 seconds. How do you find instantaneous velocity from a BT graph? You read it off the graph. The answer is 6. Brandon, pay attention, man. Oh, this should have been 100% this one, you guys.
Oh, I got something.
Yeah? V bar from 0 to 4 seconds. 0 to 4. Oh, yes. V bar on a velocity time graph, you have to find displacement. And if you didn't do that right the first time, you wouldn't get it right. And that was the answer from before, which was 24. So this area here, we already figured out to be 24 to 4 seconds. 24 divided by 4, or 6 meters per second. B. B. Oh, we didn't do so well there, but that's probably because you got it wrong before, right?
Yeah.
Probably.
8 plus 6.
Yeah. And again, it's not knowing the number that's the answer, it's being able to do it. Because when I give you a different question, you got to be able to do it. V bar from 0 to 10. Again, if you don't have that figured out from before correctly, you're not going to get this one right, right? So it's going to take that number that we had before.
21.
Was it 21? Yeah, that sounds right. 21, and we're going to divide it by d over t. 21 divided by the time is 10 seconds. 2.1 meters per second. C. Oh. Oh! Is this my mistake? V bar from 0 to 10.
It says I got the answer right.
Yeah, I know, but it says correct answer is A, but is that right? And everyone said it too.
I said C and got it right.
You said C and got it right.
Yeah, I said B, got it wrong.
Oh, there it is. It just hadn't refreshed for some reason. Okay. Correct answer is C. Good. Thank you. Okay. So, you might want to have a little review of that. I'm hoping at the very least you circled the right answers. If you don't know how to do that stuff, you need to be able to do it. Okay? If you need to spend 10 or 15 minutes this weekend reviewing, please do so. I'm done for the day. That doesn't mean leave.